My goal here is to walk through some of the basic properties of summations, but I also want to talk about reading the textbook and how to use it to get useful information. We're using the OpenStax textbook, which is a great open source textbook. So let's look at this first property. It says the sum from I equals 1 to n of c is equal to n times c. Remember, c is a constant. So this pattern is when we're just adding a constant over some range. For instance, what is the value of the sum from j equals 1 to 5 of 2? Because 2 is a constant. So to get at this, let's think about what does the sum from j equals 1 to 5 of 2 really mean? Well, it's going to be 2 plus 2 plus 2 plus 2, just with that sum written, with that 2 written 5 times, because j is going from 1 to 5. But I mean 2 plus 2 plus 2 plus 2 5 times is just the same thing as 5 times 2. And what's happening is we're multiplying our constant value, which in this case is 2, by however many times we're adding it together. So when we see this symbolic expression that the sum from j equals 1 to n of a constant value c is just n times c, that's this pattern that we could act out. It's just compressed into a symbolic form. So now let's have you try one. Suppose I ask you, what is the sum from I equals 1 to 80 of 5? So the expression is the constant 5. Don't write out 5 plus 5 plus 5 80 times. Rather, recognize that you're dealing with this situation where you're adding a constant over some range. And so it's just going to be this constant 5 added to itself 80 times. But that's the same thing as 80 times 5. So you'll get that the final answer is 400. Either one of these answers makes me happy. The key thing is I want you to recognize that this property of summations is something you can apply when you have a constant sum. The next property of sums that's sometimes useful is that you can pull constants in front. So if you have a constant that's being multiplied by your expression, you can pull the constant in front of the sum. And this is basically just the distributive property. If you looked at c times x plus y, you would know that that's c times x plus c times y. Here it's just for adding two things, but a summation is just adding lots of things. So it applies more generally. An example of how you could use this property would be, let's say that we were looking at the sum from k equals 1 to 10 of 3 times k squared. What I could do is I could pull that 3, because it's a constant being multiplied by each expression, I could pull it in front of the summation. And if I had a formula for the sum from k equals 1 to 10 of k squared, I would be able to apply it. So when you're dealing with a constant that's being multiplied by the expressions, you can just distribute it out and pull it in front. As an example of how this could work, let's look at the sum from k equals 1 to 19 of 5k. I have this constant 5 that's being multiplied in front, and so I can pull it in front of the summation. So I have 5 times the sum from k equals 1 to 19 of just the expression k. Now how does this help me? Well, this sum from k equals 1 to 19k is the 19th triangular number. It's the sum of the first 19 positive integers. And I remember that I have a formula for that, which is going to be 5 times this expression will become 19 times 20 divided by 2. So to calculate and get my final answer, I would just need 5 times 19 times 20 divided by 2, and whatever this simplifies to would be the final answer. The key idea here is when I have a summation and there's a constant multiplied by the expression, I can pull it in front. Let's look at this third property, and this is the last one we'll do. But the sum from I equals 1 to n of ai plus bi is equal to the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi. It's a lot of symbols and it may look really complicated. But all it means is that we can split sums. So we're looking at a sum, and inside the sum there's two things added up. And we can just split those up. So this might look like something you would expect that you could do. And in order to justify why it's true, let's think about what it means when we're summing up two things that we're actually adding. As an example, let's look at the sum from k equals 1 to 4 of k plus k squared. If I actually wrote out what each of these terms mean, what I would get is that this is equal to 1 plus 1 squared when k is equal to 1, plus 2 squared when k is equal to 2, plus 3 squared, plus 4 squared. But because of addition and the properties it has, I could rearrange these terms. And so I could rewrite the 1 plus 2 plus 3 plus 4 part as its own thing. And I could write the 1 squared plus 2 squared plus 3 squared plus 4 squared part as its own thing. And then these two summations, each of which is its own thing, will give me the opportunity. So now I have two long lists of additions. I could rewrite each of these as a summation. So this first one would just be the sum from k equals 1 to 4. Okay. And this other piece would be the sum from k equals 1 to 4 of k squared. So here's an example of why this works in practice, where I'm taking the two sums and I'm splitting them up. Those are the basic properties of summations. I wanted to give you an example of what it looks like to go through the textbook and expand it a little bit so that we have more complete information that we understand.